Hey everyone, it's Timmy Gobbles, and today I'm going to be finishing up the Proc Gen caves I've been working on. So we're starting off from the last video. We've got these boson disk samples, and we want to get to here. We want to get to these wiggly squiggly caves. And then, just to top it off, we want to import this into our scene where we get to dig around and stuff. Maybe import's not the right. So let's look at these boson disk sampled points. And I want to group them. I don't want all my caves connected. I want some caves in groups and some not. So I'm going to put maybe like 4 random points, and then I'm going to group my boson samples based on how close they are to these random points. Then I'm going to shift these points to the center of each of these groups and hopefully remember where they were. Okay, that's pretty good. And then we're going to do the whole process over again. We're going to regroup the points, and some of them move, some of them don't. And we're going to repeat that until we're satisfied. So you just keep iterating of shifting the centers, regrouping the points, shifting the centers, and so on and so forth. So let's look at the code. So we're going to pass in the points we want to group, the boundary, the number of groups, and the number of times we're going to iterate. And we'll spit out the grouped points. Now we need an array that keeps a track of which group each point is in, and an array that keeps track of how many points are in each group. Next, we needed to initialize the group centers to random points inside of the boundary rectangle. Now let's look at the loop. We want to do this once for each of the number of iterations. For each point, we want to assign it to the closest group center. Next, we want to find the average point in each group, and that will become the new center of that group. That ends the loop, and now it's time to package grouped points into their own array. And once we have them all packed up, we'll send them out. It's a pretty simple algorithm. I don't remember its name because I learned it in some random class in college, but it works good enough. So now that we have grouped points, we need to do our minimum spanning tree. So to start off, we're going to get a Delaney triangulation of the group of points. And then let's put the points back on there. So now we want to pick a random point. We're doing Prim's algorithm, by the way. So we look at all the possible connections we can make with our set of connected points, starting with a random one. We want to pick the shortest path. So the shortest path is going to be this one on the left. So now we have 2 points in our possible points to play with. We want to look at all the connections we can make and pick the shortest one that connects a new point to our graph. So then we can just go through here and kind of eyeball the shortest ones until we've connected every point. Now, the reason why we need the Delaney triangulation is look at how many comparisons we have to make if we look at every point in our group of points. It gets very, very messy. So the Delaney triangulation cuts down on the amount of work we have to do. All right, so let's look at the code. So we need to pass through our group of points, and we're going to spit out an array of pairs of points that represents the connections. So for first to do the Delaney triangulation, we're just going to go use the geometry class, and it has a Delaney triangulation right here. And since we don't really care about the triangles, we just want the edges, I'm going to break up those triangles into vectors that represent the 2 points connecting each edge. And I don't want to add any duplicates. Next, we need to find the length of each of those edges. That way we don't have to calculate that over and over again. Next, we need to initialize our arrays of our queue and put 1 point into it. Now let's go ahead and look at the loop. For each point in our queue, we want to look at all the possible edges that include that point. Then we're going to find the shortest length edge and keep that index. Then we're going to add that edge and the new point that it connects to our queue and our output. And we can remove the edge from all of the edges and the length edges. All right, so let's see how well this does. Ooh, it doesn't look very good. It doesn't look like it's connecting the nodes like I want it to. So I had to spend a while fixing this, and it turned out to be the issue was my Bressenhams. And so here we're just looking at one of the grouped points. So I kind of played around with Bressenhams, and the problem was if you changed the inputs, it would create a different line. So here I just flip-flopped them, and it didn't make the triangle. It made a little hat thing. So the fix for this was to fix the starting Y or X value based on which was larger and which direction I was going. So if you're copying my code, you might want to figure this out or test it yourself would be even better. And then, yeah, it kind of depends on whether I'm looking at as shifting the X value or the Y value. Okay, and once we fix Bressenhams, look at that. Look at those caves. Aren't they blocky? Don't they suck? We need to soften them up a bit. So first, I did a couple of helper functions to fix some of the issues I was having. First is to know what layer I'm looking at. And since I'm going to be adding tiles back in, I wanted a quick function that could help me. So this is going to tell me what piece of the tile set I want to use on the tile map based on the location. And then this is going to get used later when we want to put our player at the ground level. So I can use this function to find it based on their X value. All right, so those are the helper functions. Added new noise rules for the stone and the bedrock, just to kind of finish that off. But I mean, it's the same as doing it for the dirt, so. Okay, so what can we do to soften up those caves so they're not so liney? So we're going to use Cellular Automata, and what this does is, for each tile, it's going to look at its neighbors and then decide what to do with that tile. And so it's a very expensive algorithm. But once you see the results, you're going to be like, ooh, wow. So we need a rule. We need a rule based on what the neighbors are. Oh, and it made it recursive instead of iterating it in a loop. So maybe this is bad. Maybe it's good. I don't know. It's probably more expensive on the memory. What to do about that? I don't know. And I tried doing it point by point instead of just iterating over the whole tile map, but it actually ended up being quicker just to iterate it over the whole tile map. So go figure. All right, so looking at the rule, and we only want to look at tiles that are empty because I'm going to make my caves wide and I'm going to fill them in a little bit. So I got those values from this paper about procedural generation story stuff. And see, they have this path that's all blocky and they want to make it nice and smooth like I want to make it. So these were the probability values that they ended up using. So you got 0 and 2% and all that stuff. And then look how nice those caves looked. Look at that. They're just beautiful. And I think the goal of this paper was to make like a procedural generated Pokemon game. So that was pretty cool. So then here, I sped it up 4 times fast so you can see how slow it is. But look at that. It really takes those boxy caves and cleans it up a lot. And it's a little funky in some areas where it looks a little repeated, but overall it looks pretty random. So here I have this little time lapse of it doing the Cellular Automata one step every like couple seconds or so. So you can see how if you go too far, you actually lose some of the caves. And then here I have it doing like a couple steps at a time instead of just one. So it's kind of up to you to figure out how many times you want to apply it. All right, so now that my cave generation kind of works, I need to get it to work with my main scene. So I'm going to kind of just copy and paste all this code into a new class called World Generator. And then I'm going to try to make some kind of function. I usually like calling it do the thing. I don't know. It's stupid, but it works for me. And it's just going to do all those steps we did, but I can call it in main. And there's a little bug there. Oh yeah, I need the player location wasn't right. Okay, so there we go. Now I'm playing with my randomly generated cave, and it spawned me on the ground, and then I fell a couple feet because there was a cave right where I was. So maybe you need to remove some of the nodes that are near your player spawn. Maybe those need to be not part of the cave generation, so you don't end up falling through the world or something like that. There's probably more tweaks to be made, but I think this is a really good start. And I'll speed this up a bit so that we can all have motion sickness. And yeah, I was just like really glad how well this turned out, and you know, I can kind of dig the stuff, and it sort of looks cavey. One thing is somehow I need to make the cellular automata faster. It's too expensive. Yeah, but overall, I'm really happy with it. If you guys have anything you want me to do in the next couple of videos, let me know. But other than that, I'll see you all next time.